Hello, everyone. Time for chapter 4, correlation and regression. We're starting to get into some more interesting territory here. But from here on out, we're basically going to assume that you're well versed in the notion of a p-value, a null hypothesis, and all of the associated concepts like statistical power and sampling error. So if you're not feeling super confident with those, you still might be able to follow along here, but I'm not going to necessarily go too much into that other stuff where I'm just going to kind of assume you already know that. So a correlation coefficient, which is usually denoted with a little r, lowercase r, can range from -1 to +1. When r, or the correlation, is equal to -1, that means as one variable goes up, the other one goes down by an exact predictable amount. That means there's a perfect linear negative relationship between the two variables. When the correlation equals +1, that means there's a perfect positive correlation between both variables. As one goes up, the other one goes up by an exactly predictable amount. When there's zero correlation, that means the two variables do not coincide whatsoever. You cannot predict one from the other. It's just if you do a scatter plot, any given x value can be associated with any given y value. There's no telling. Most correlations, are not anywhere close to perfect +1 or perfect -1. So here's an exact positive correlation of +1. As x goes up, y goes up exactly some amount. Even in psychology, this correlation of 0.8, see, it doesn't look like a straight line like the +1. It looks like a cloudy straight line at 0.8. When you go to 0.5, the line gets cloudier. 0.2, so we're getting close to 0, the cloud gets even cloudier. You can barely tell that as x goes up, y tends to go up a little bit. So a correlation coefficient is basically a way of quantifying the degree to which two variables coincide together. And in psychology, many of the variables we deal with are closer to this 0.2 range. There is a slight tendency as x goes up, y tends to go up. So like GPA and self-esteem, let's say self-esteem is y and GPA is x. When GPA goes up, self-esteem tends to go up, but not everyone bases their self-esteem on GPA. So you might have someone up here with a very high GPA, but they're nonetheless not all that high in self-esteem. It's just a very general cloudy trend. Let's take some hypothetical data here. I just noticed there's a mistake. Fix that for future reference. Let's say you have some data here. Self-esteem, this is a made-up self-esteem scale. The lowest score is a 20. The highest score is a 40. That doesn't necessarily mean that whatever this made-up scale is can't go lower than 20 or higher than 40. But let's say you got 8 subjects. Each one gives us a GPA and a self-esteem score. If you were to calculate the correlation between these two scores, let's see if I can find where it is. Well, it turns out I never put a visualization for that correlation. Whoops. But if you calculate the relationship here between GPA and self-esteem, there is a correlation of 0.33. But just because you observed a positive correlation or a negative correlation, and even if it's a fairly large one, that doesn't mean it's statistically significant. You could happen to draw samples that misleadingly appear to be more correlated than they really are. It's also possible to to just randomly draw a sample where they appear less correlated than they really are. That's why you need to do a statistical test. I have the 95% confidence interval here. You might remember that from previous chapters. So basically, I observed a correlation of 0.33 between GPA and self-esteem in this sample, but the 95% confidence interval says, well, it was 0.33 this time, but it could have been as low as negative 0.49 or as high as positive 0.84. You'll notice that 0 is within this interval. The bottom value is negative, the top value is positive. That right there tells you that it's not statistically significant. When you do a test to see if a correlation is statistically significant, you end up using a t-score. T with the degrees of freedom 6. That's the number of, if you're in psychology and you're studying people, it's going to be the number of people minus 2, or the number of pairs of observations minus 2. So if there's 8 pairs, you'd be at 6. It might be easier to just think of, if the unit of analysis is the person, then it's the number of people minus 2. So we'd have 6 degrees of freedom in this little tiny data set. So we're dealing with a t-distribution with 6 degrees of freedom. You have to plug in a parameter since, and you use the t-distribution to test correlation coefficients. The null hypothesis is that there's no correlation, and you want to know, do I observe a correlation large enough in absolute value, meaning it can be very high or very low? Is it extreme enough? Is it far enough away from 0 that we can conclude that it's not 0? So the t-value represents how far from 0 it is. Our null hypothesis says that the correlation is 0. There's no relationship between these two variables, but if the null hypothesis is true, you're going to occasionally see a t-value that's slightly higher than 0, slightly lower than 0. I'm not showing you the equations to turn a correlation coefficient into a t-score, but the t-score that's associated with this sample is 0.86. So we are 0.86. We've got a t-score of 0.86 up here. I've highlighted the area under the curve that is at 0.86 or higher. And then I've got negative 0.86 and lower highlighted. So these two highlighted regions jointly represent, like, what's the probability of getting a 0.86 or higher and a 0.86 or lower. And that ends up adding up to 42%. So if the null hypothesis is true, there's a 42% chance that we'll see a t-score that's higher than 0.86 or lower than negative 0.86. That's what the p-value represents. Tattoo this to your brain. The p-value is the probability of observing your data or more extreme data when the null hypothesis is assumed to be true. You can tell from this, hopefully, that we cannot reject the null hypothesis. P would have to be less than 0.05. That means that when you assume the null hypothesis is true, the probability of your data or more extreme data has to be less than 5% likely for you to reject the null hypothesis. And we wouldn't be able to reject it in this case. Now, if you cheat, never, never, ever, ever do this in real life. This is just to make an example. But if I took this data and I multiplied it by 5, like if I took these same 8 subjects and pretended like, okay, I have 5 of each of you, 5 of subject 1, 5 of subject 2, 5 of subject 3. So you end up looking like you have 40 subjects. That increase in sample size would change your results. See, I'm kind of cheating here just to make a point. But if you have a higher sample size, you would have the same correlation. It would still be 0.33 correlation between GPA and self-esteem. Now my degrees of freedom go up. My t-distribution is going to change shape. That means any t value you observe on the t distribution has a different probability associated with it. In addition to that, my 95% confidence interval changed. It was a pretty wide interval going from negative 0.49 to positive 0.84. Now we got a correlation of 0.33, and the confidence interval says it could have been as low as 0.02 or as high as 0.58. So it doesn't contain zero. We just barely got away from zero at this 0.02 as the lower boundary of the 95% confidence interval. And P equals 0.036. That means there's a 3% chance that you would observe data, a t-score this high or higher, or data this extreme or more extreme. When you assume the null hypothesis is true, there's only a 3.6% chance of that happening. Actually, I think I messed up. The t-score is 0.86 over here, but over here, I put the correlation as 0.33. So I don't remember exactly what the t-score is. It's not 0.33, that's the correlation. But whatever the t-score is, it's a little bit above 2. I can see, I've got plotted here a t, let's say it's 2.5. I don't know, it's probably not 2.5. It's probably about 2.2. That's what it looks like. The probability of getting a t-score of 2.2, let's say, or higher, that interval is highlighted right here. Probability of getting something negative 2.2 or lower is highlighted right here. So if my null hypothesis is true, then I should see a t-score of 0 or close to 0. And what I got is this observation where it's like, if I see something that extreme or more extreme, there's only a 3.6% that I would land either in this tail, in this little gray interval here, or this little gray interval here. There's actually a 1.8% of getting this high or higher, and a 1.8% of getting this low or lower, but you combine them together since this is a two-tailed test. Overall, there's about a 3.6 probability that you'd observe a correlation with a t-value this high or higher in absolute value. So we would reject the null hypothesis. We would say, well, there must be an actual correlation, because when you assume there is no correlation, our data look very improbable, but we know our data are real. Well, in this case, they're not real, but you know, if they're real. Boy, that's confusing. So I had y'all do a Rotten Tomatoes example where you went and looked at just the tomato meter scores themselves. Here we have a correlation between tomato meter scores and the release date of the movies. And this is for Quentin Tarantino. So I've got each movie's tomato meter score as the y-axis here, and the year of release is the x-axis, and I've got each movie plotted. And as you can see, there kind of looks like there's a downward trend over time. I put this little line here. There's actually a good reason for that, but I'm going to get into that in the regression point. At this point, it kind of shouldn't be there because this is just correlation. I observed a negative 0.44 correlation between tomato meter scores and release date, but the confidence interval is very wide. It has a negative number and a positive number. That means it's automatically not going to be statistically significant. And the t-value with 8 degrees of freedom is 1.4. There's about a 20% chance of seeing a t-value that extreme or more extreme when you assume the null hypothesis is true. Therefore, we cannot reject the null hypothesis. That means that we cannot conclude that Quentin Tarantino's movies are getting worse over time or better over time. This is a two-tailed test. We have to retain the null hypothesis. The null hypothesis is that there's no correlation between tomato meter scores and year of release. Now, if I do something called p-hacking, what's p-hacking? Well, you want your p-value to be less than 0.05 because then you have a statistically significant result. And even today, there is a bias in publishing, academic publishing, research publishing, where if people don't see a statistically significant result, then they think it's not interesting enough to publish. I actually kind of agree with that because even if you do observe a non-significant result, if p is above 0.05, that is possibly interesting, but it might just be because your study was underpowered. So you have to demonstrate that your study had adequate power, or probably had adequate power, which is a whole other thing I'm not going to get into. Suffice it to say, people want their p-values to be low because if you get p less than 0.05, that interests more people. It seems like a more interesting thing. You might get your research published if p is less than 0.05. So people do sneaky things sometimes to try and get that p-value as low as they can. One of the things you can do is you can go question which data points should be allowed in the data set and which ones shouldn't be. And you can come up with good reasons for removing Quentin Tarantino's Death Proof from the list. You could say it doesn't really count as a movie. It was a short film. It's a very long short film. But you could say, hey, if Death Proof counts, then why shouldn't the commercials that Quentin Tarantino's directed count? Why should the music videos count? I don't know if he directed any commercials or music videos, but if he did, you might say, why don't we just keep it to true feature-length movies? When you do that, this relationship seems more close to a linear correlation. See, instead of, that's Death Proof down here. That kind of ruins the general trend. You take that out, it looks more like a straight line. And when you look at the t-test for that correlation coefficient, it's so close to 0.05. It's 0.062. Just so close to being a statistically significant negative correlation. Not quite. Let me pick on M. Night Shyamalan a little bit. I think it's fascinating how bad M. Night Shyamalan is, in my opinion. If you're a big M. Night Shyamalan fan, sorry, you might want to trigger warning. I'm about to insult your favorite person. M. Night Shyamalan is said to have started off really good. So he directed The Sixth Sense, was his first real movie. That was around 2000. That's it right here. Technically, he directed something before that, and it was apparently not very good. But I think that's like not considered one of his main movies for some reason. But people used to say M. Night Shyamalan started off pretty good with Sixth Sense, and he made a couple other movies that weren't half bad, but then it just got really terrible after that. I think his low point was The Last Airbender, which I've never seen, but I've seen enough M. Night Shyamalan to it's hilarious how bad his movies are. There's almost a negative correlation, a correlation of negative 0.22 in psychology contexts is it's not bad. But as you can see, it's not, it's a very cloudy. If it is going down, it almost looks like it's going down and then coming back up. Some people say M. Night Shyamalan kind of hit a low point and then recovered. You can test that, by the way, but we're not covering how to do that in this class. If you just take his entire filmography and do a t-test on the correlation between his tomato meter scores and the year each of his films were released, you get negative 0.22, but it's not statistically significant. T with 12 degrees of freedom is negative 0.79. The p-value associated with that is 0.443. It's not low enough to reject the null hypothesis. Now, if you take out everything that came after 2013, see, that might be when people said, oh, well, that's when M. Night kind of rebounded and started making good movies again. I've heard a lot of people say, have you seen Split? I have not seen Split. People said, oh, Split was so good. And, M. Night, turns out he's still got it. He's still capable of making good movies. Hey, maybe Split is good. I still think M. Night Shyamalan is garbage, but Maybe split is like good garbage. The Sixth Sense wasn't bad, but I mean, anyway, this isn't an M. Night Shyamalan class. Let's see what happens when you p-hack. You want your p-values. So you take out everything past 2013. Now we have a negative correlation of negative 0.77. And look at this 95% confidence interval. It's still a wide interval. It could be as low as 0.94 or as low as 0.28. But notice that the interval itself does not include zero. They're both negative numbers, and it is statistically significant. P is less than 0.05, it's 0.008, meaning that if you were publishing this as a study, you could say, hey, look, M. Night Shyamalan is getting worse over time if you stop at 2013, P less than 0.05. I would reject this. I mean, apart from the fact that it's just one director and it's not really of scientific interest, whether M. Night Shyamalan's getting worse over time, it would nonetheless be a statistical analysis that had a statistically significant result. And that, in many cases, passes as scientifically interesting. So yeah, correlations have a couple of assumptions. One of those assumptions is that the relationship between the independent and dependent variable is linear, meaning that they go in a straight line. You cannot have a curvilinear relationship. And you are assuming there are no outliers in the data, which you could play with certain things. You could say, well, Death Proof is an outlier, from the Quentin Tarantino example. But basically, I think this is called Ansom's quartet, is a set of data sets that all have the same correlation between the X and the Y variable, the independent and dependent variable. But it's clear if you look at them that while they're all very different data sets, they all have the same correlation, but it's clear that they don't all fit the assumptions of a correlation analysis. Correlation analysis assumes there's a straight line. It can be a cloudy straight line, but there is a straight linear relationship as X goes up, Y goes up, and there's no outliers. We've got that in this top left data set. In this top right data set, we're not matching the linearity assumption. This is not a straight line. This is a curvilinear relationship. So a correlation analysis is not really appropriate. You would want to do a curvilinear, you'd want to do a different test that acknowledges that there's like a quadratic relationship. We're not going over that in this class though. And this bottom one down here, you've got a straight line between most of the data points, but then you got this one data point up here that's pulling the whole linear relationship off kilter. Same with over here, there's actually no linear relationship at all. All the X values are pretty much the same and have a bunch of different Y values, but they're not linearly related. But you have this one outlier over here that makes the entire trend appear linear, because this R value, this correlation coefficient, isn't like eyeballing it to make sure it's linear. It's an equation that's applied and you get a number out. You know, you put numbers in, you get a number out. Only a human can really look at these and tell you whether they're actual linear relationships or whether there's an outlier that's influencing whether the relationship appears more correlated than it really is. And this bottom right here one is a great example of how if you ran a correlation analysis on this data, this would look like a really large correlation, and you could probably publish that. And if you didn't plot it, maybe no one would ever know that this is not actually, these variables aren't actually correlated at all. Everyone's basically at the same level of X, but different levels of Y, so there's no relationship. You just have this one person who makes the whole thing look like it's linearly related. So assumptions are important. Make sure you check those, plot your data, check that out. I'm going to quickly go over simple linear regression, because simple linear regression is basically exactly like correlation, except instead of quantifying the degree to which two variables are related, you're also using one variable to predict the other. And this is done by using a straight line. An equation for a straight line comes in the form of y equals mx plus b. That's the m is a slope, x is you plug in x, and we're going to cough out a y. But you also need an intercept. Y-intercept is where does the line cross over the y-axis when x equals 0. Here's an equation for one line, y equals 1/2 x plus 2. It's a line with a positive slope, and it crosses the x-axis at 2 when x equals 0. This line is y equals negative x plus 5. It has a negative slope, it's going down, and it crosses over when x equals 0, it crosses over at 5. Hopefully you have some familiarity with slopes and intercepts. It's really the slope that's the important part for this class. The intercept is not that important, but if slope is positive, it's going up. If it's negative, it's going down. If it's 0, it's side to side, not really going anywhere. That's really the most important part for the purposes of interpreting simple linear regression analyses. We call it simple linear regression because we only have one line. There are situations where you can have a very flexible equation that changes the line a lot depending on different variables. But here we only have two variables. You have y, the dependent variable, and you have x, the independent variable. We call it linear regression, simple linear regression, because it's a straight line. And just like with correlation, we assume a linear relationship with simple linear regression. We're using the equation for one straight line, and we're using x to predict y. And with some slight rearranging, instead of y equals mx plus b, you have y hat, which just means my predicted y value, equals slope b sub 0 plus x times, no, b sub 0 is the intercept. So predicted y hat equals the intercept, or b sub I, or b sub 0, plus x times the slope, b sub 1. It's the same thing. Slope times x plus b is the same thing as b plus x times slope. We change slope from being an m to being a b sub 1. We change the intercept from being a b to being a b sub 0. Same thing though. And we're basically saying, hey, if I plug in an x value, can you give me an intercept and a slope such that when you crunch these numbers, we get a predicted y value? And the line in simple linear regression represents our best prediction. For any x you plug in, the line is all the y's, my predicted y's, my best prediction. I'll give you some examples. So this is the Quentin Tarantino example. I have x is the year of release and y is the tomato meter scores. And when you pick a intercept and slope combination, you get a line that constitutes your best predictions. If you reveal, Quentin Tarantino actually directed a movie 8 years into his career that you didn't have in your original data set, what do you predict the tomato meter score for that movie was? You don't know what exactly that tomato meter score is. You'd use the regression line. You'd say, well, the line for the 8 comes out right here, so that's my prediction. You choose a slope and an intercept that basically comes as close to all the data points as you can, so that you make the best predictions. In other words, you want to minimize prediction error. Prediction error is the distance between the regression line and the data points. So the regression line tries to come as close to each point as it can, but it's going to have to miss some of them by a little bit. So his first movie, what was that? Reservoir Dogs, was very highly rated. The regression line predicts that it's very highly rated, but not quite as high as it actually ended up being. So we have this little teeny tiny red line representing how much we underestimate Reservoir Dogs when we make our predictions. Pulp Fiction, again, the regression line underestimates it. So you got this little red line representing that. Jackie Brown, was that his third one? I don't remember. Jackie Brown is actually almost right on top of the line. So is whatever these are. Kill Bill came out at some point around here. Death Proof was very far below the typical. So the regression line is the line that minimizes these little red lines, these prediction errors. Death Proof was a big overestimation if you're going off of the regression line. And then everything else is pretty far off the line, but still staying as close as possible. So when you choose a intercept and slope combo, you want any X that gets plugged in to be as close to these points as possible. You want to keep the length, the total length, if you were to add up the length of all these red lines together, you want to keep that total length to a minimum. Another word for these red lines are residuals. Residual means leftover. We want to keep the residuals as small as possible. And regression is actually, I don't go into the math in this class behind it, but the equations that give you the intercept and the slope are based around trying to minimize the squared residuals. So if you took each of these lengths of residuals, leftovers, mismatch between the regression line and the actual data points, and you squared each of those points, added them all up, we want to minimize that. We'll pick a slope and intercept combo that gives you a line that keeps the residuals as small as possible. So when you crunch those numbers, you end up with a slope of, I keep doing that. You end up with an intercept of 89.49 and a slope of negative 0.42. So just to unpack that a little bit, that means that when Quentin Tarantino first started making movies, it's been 0 years since he started. The regression line crosses the y-axis at 89.49. It basically just means that, like, when he first came out, he was already making movies that were pretty darn good. But for each year that comes out, each time X increases by 1, our predicted tomato meter score goes down by 0.42. It's a negative slope. We're decreasing our predicted tomato meter scores by 0.42 tomato meter points each year. So what is our prediction when Tarantino is 5 years into his film career? We do intercept 89.49 plus, we plug in 5 for X, multiply 5 by negative 0.42, and we end up with a prediction of 87.39. That's really close. I think this is Jackie Brown, was just a little under 87.39, but very close. Plug in 10 instead of 5, and you end up with 85.29, and that again is really close. Well, he didn't make a movie 10 years into his career. It looks like he made a movie 11 years into his career. But if he was to release a movie 10 years into his career, you don't know where exactly it would be. So I guess maybe we weren't technically close. You can plug in any X you want. You can plug in a negative X. You can plug in an X like how good is Tarantino's movies 100 years into his career? He probably is not going to have a career of 100 years. But you plug numbers into an equation, you'll get numbers out. And in Quentin Tarantino's 100th year of making movies, our regression equation says that his predicted tomato meter score is going to be 47.49. So it takes Quentin Tarantino, if our regression line was like taken to be a very good model of Tarantino's movie qualities over time, then it takes Quentin Tarantino a very long time to start making bad M. Night Shyamalan levels of movies. So the intercept and the slope are subjected to statistical testing. We use the t-test, and honestly, doing a t-test on the intercept for a regression equation doesn't usually have much of a purpose. So T with 8 degrees of freedom is 19.22. That is a very, very big T score. P is very far less than 0.05. It's actually less than 0.001. Well, what does that mean? That means we can reject the idea that the intercept is actually 0. Not very interesting. That just means that Quentin Tarantino didn't start at 0 whenever his career started. In many circumstances, an X equal to 0 doesn't actually make sense. Like, you cannot have an IQ of 0, technically. I don't think IQ tests are valid if it's giving you scores that low. I mean, there are many circumstances where it just doesn't make sense to have an X that's even anywhere near 0. Just depends on what kind of data you're dealing with. The intercept is probably just not going to be that interesting. What is interesting is the slope. As X is going up, is Y going up or down? If the slope is close to 0, then the regression line is going to be flat, meaning that as X goes up, Y does not tend to go up or down. Here we have a negative slope of negative 0.42, meaning that for every increase in X, we have a negative 0.42 unit decrease in Y, or predicted Y. That is negative. That's what we actually care about, but it's also not statistically significant. With such a small sample, we do see that the slope is negative, but we can't be that confident that maybe this isn't just a fluke. Lady Luck could be playing a trick on us. It could be the fact that this is just a random sample where it just happened to look like there was a negative slope. We can't rule out that there's a 0 slope, which is flat, and there might even be a positive slope. You don't know. It's not statistically significant. We have to retain the null hypothesis. The null hypothesis here is that the slope equals 0. One thing to keep in mind, and this is kind of an advanced point, but I don't know, I've seen people really make this mistake before, and I feel very embarrassed for them. So I just want to point out that the equation for the slope of a regression line is, if we're talking about simple linear regression, there's one independent variable and one dependent variable. The equation for that slope is just the correlation between those two numbers times the ratio of the standard deviations, standard deviation of Y divided by standard deviation of X. If you were to flip it around and let's say, instead of trying to predict tomato meter scores from the year, what if you flipped it around and say, you give me a tomato meter score and I'll predict what year that came out? That's not going to change the slope at all, because in simple linear, I mean, the slope is going to change, but the slope is based on the correlation. The correlation does not change. We're just changing whether it's S of Y divided by S of X, or whether it's S of X divided by S of Y. The statistical significance of the slope is not going to change. The slope might change from being positive or negative, but the slope is determined really by the correlation coefficient. And the reason I'm harping so much on that is because I was at a conference once where someone said, oh, we have this variable X and it was positively associated with this variable Y. So we have this theory that X causes Y for these reasons. And someone in the audience asked a very basic question. They said, how do you know Y isn't causing X? Very simple question that anyone should anticipate if you're ever presenting research, especially correlational research. And this poor guy, I still, to this day, he might not even know how bad what he said was, but he said, oh, when you run the regression X predicting Y, it's statistically significant. But when you do Y predicting X, it's not statistically significant. Therefore, X is causing Y and Y is not causing X. To this day, I'm still just so ashamed of that guy. Horrible. No, in regression and in correlation, if we're talking about simple linear regression, X and Y, does not matter. The slope is going to be statistically significant or not statistically significant. Whether you're predicting y with x, or if you're using y to predict x, flipping it around, the statistical significance of the slope is not going to change. So don't make that mistake. All right. That was a quick overview of chapter 4. The little write-up I did goes a little deeper into it, but I think this is a good place to start and is about on the level of the exam questions you'll get. I'll see y'all next time. Bye.